Welcome you all in this session. In the very first, I'm going to talk about the finite element estimation. Then I will talk some application of FEM in biological problem. As the title of this STTP is what? Solution of differential equation using numerical method. So in the very first lecture, I will tell about the finite element estimation or method analysis. Little bit I will compare with the other existing method also. In the first hour, I will introduce the introduction of FEM, some problem we will solve, a small problem we will solve. And in the second hour, we will talk about the biological problem. So once we it is introduced by Dr. Chandrasekhar. So this is the outline of my presentation here. Background of numerical method, solution of differential equation. It should be by FEM. Calcium signaling, some biological problem. FEM of calcium signaling that we see. And computational finite element method will be introduced also. Some references that we will see here. So once we talk about finite element methods, it is a very old method, we can say. It is developed by civil engineer. In current scenario, we cannot stop up to the finite element method. So those who wish to go up to that level, so it is finite element analysis now. So the finding the solution of differential equation, that is a finite element method. But if you analyze the solution, analyze the method, that termed as a finite element analysis. Nowadays, including finite element method and analysis, since the physical problems are very complex in nature, so in that case, we use some software also. So computational finite element method is also required nowadays, especially in the biological problem where we are working. We use this computational finite element method. Some books in the introduction we required for the beginners. Here you can see the SS Rao, the finite element method in engineering. So for the beginners, you can go through this. Desai and Shah also is very good. If you want to go for the programming point of view, so MATLAB is there, non Bang that you can study. And if you are going for the application for engineering application point of view, so JN Reddy is very good for study. So I recommend SS Raw, you need to study because chapter wise, point wise, it is very well defined. Now, once we talk about the finite element method, definitely we thought about the numerical method. Why numerical method is required? Since this is the first lecture of STTP, that's why we required to talk about some requirement, necessity of the numerical method. So as you know, the most of the phenomena in science and engineering that are described by the ordinary and partial differential equation. And these partial differential equations as well as ordinary differential equations can be solved by classical analytic method. So sometimes it is impossible to solve such a problem which is complex in nature, highly nonlinear. So numerical methods like finite difference method, finite element, finite volume, that we use to solve such partial differential equation. But the thing is, once we solve, it is approximate solution in nature that we get. So once if we are not able to find a solution, that is definitely we require a numerical method to get the solution. At least we can get the solution. Second thing, even analytic solution is available. Also, we go for the numerical method. Sometimes we give advantage to numerical method over analytical method. I will come to in coming slides why it is required. Some engineering application that you can see for the application of numerical method for solving engineering problems like stress analysis, heat transfer, fluid flow, electromagnetics. These are solved by the computer simulation and the numerical method are used in that simulation. FEM can be used for the behavior of the structural, mechanical, thermal, electrical, and the chemical system for both design and performance analysis. I will focus more on FEM than other method, but sometimes we require to analyze why FEM is required. So first we will talk about the analytic and numerical. We can compare with the analytic and numerical method. To solve a partial differential equation with initial boundary condition, we need the solution which is particular in the problem. So we can solve analytically the homogeneous in nature in geometry that can be solved. Numerical method that replaces the PDE partial derivative with the algebraic equations. So one solution can handle multiple problems that we can see. The heterogeneous problem can be also handled with the complex geometry that can be handled. Once we talk about the accuracy, analytic, no question, no doubt about the accuracy in the analytic solution, but in the numerical method, usually we get the approximate solution. So continuous solution may not be applicable as algebraic or discrete point of view that we go. Okay, other method regarding the numerical method that we can see the finite difference, finite element, finite volume method, spectral method that we can say differential quadrature. Other methods are also available that can be handled the nonlinear problem or some differential equation, whether analytic solution is available or not. But once we talk about this number of numerical method, every method has some plus points, some negative points. So we can't say which method is good according to problem. According to situation, we require to go for the problems, go for the solution. Suppose if we talk about the heat equation, I am talking about the okay, just a minute. Okay, so if we talk about the suppose heat equation, so we know it is suppose del U by del T is equals to some coefficient C square del 2U by del X square and some function that can be added. So what we see, if we require to study this heat equation, it is well-known physical problem that we can define. Suppose we require to study in the one-dimensional case. You know, analytic solution is available, even though you can apply the finite difference, finite element method can be applicable. If we add here the second dimension, that is del 2U upon del Y square. So in the coordinate system, your domain will be like that initially, X and Y direction that we can represent here. Suppose you are applying the finite difference method. So what we do usually, we divide whole the structure, whole the geometry in the form of with the node value. So at the nodal point, we will apply the finite difference method and solve accordingly. So once we increase the number of node, the accuracy will be increased in the finite difference method. The thing is, in which case we can apply finite element method. Later on I will come if the solution exists, definitely we required to go for FEM. So in finite element method, what we do, we discretize whole the region in the form of element. So this is small rectangular shape that you can see, it is called element, and element wise we will solve the problem. Element can be different. Suppose we wish to take the rectangular, that can be possible, including rectangle and triangular element, that is possible. So in which case FEM has advantage over the finite difference method. Suppose if your geometry is like that, in that case finite difference fails to give the solution because it required the regular geometry. Either you can approximate by having some regular structure, but your problem is in the nature irregular. In that case, you require finite element method first. This is the first requirement to go for the finite element method. You can discretize whole the domain in any irregular point of view that you can discretize, and you will get the solution accordingly. Second thing, if we are talking about this one-dimensional diffusion problem or heat equation, suppose if you are talking about the straight line only, in that case, finite difference have the advantage over the finite element method. But if this one-dimensional flow have some like pipe flow, if we are talking about, so in that case, finite element method, okay, you can use, but geometry is what it is a three-dimensional geometry, and your equation is in the form of one-dimensional heat equation. So that is the beauty of finite volume method, that can be handled. The pipe flow, the actual pipe flow can be handled with the help of finite volume method. If you have the different cross section here, suppose this is like that. So in that case also finite element method is very helpful to solve the problem. Now come to the analytic solution. So analytic solution always give you in the regular geometry form, whether it is the coordinate system or in the polar form. So either it can be the square or rectangular or a cube or cuboid, or you can draw the circle, cube, circular surface, sphere, hemisphere, that can be applicable. But if suppose I draw like that figure, this star shape, suppose I talk about this. So in that case, analytic method fails to give the solution. So in that case, finite element method is required. So I hope so. I'm clear with the finite element method, why it is applicable. Then how we proceed in the finite element method, that we will move accordingly. Just a minute. Oh, slide is not moving. Okay. So finite element method that I will talk about first, then we will talk about the finite element analysis and computational finite element method. So if we consider such type of region, so what we see, we require the finite element method. So this is the actual region where we will use the triangular type of element. And first we talk about the such type of discretization is involved. You can define your element. So once we talk about the element, so it has a node. If it is triangular, it will have the 3 node. If it is the rectangular, it will have the 4 node. So the node is very important in the calculation. You can define the mesh. Find the base means what? You will have the small pieces of elements. If your geometry, if you have irregularity is high, then you can go for the small pieces, a small element. So refinement, once we talk about the refinement, it means we are talking about the finite element analysis also. So that we will come to in the upcoming slide. So what are the requirements for the analysis point of view in the FEM? So a classical method like separation of variable, Laplace Fourier transform, that can be applicable to solve such partial differential equations. But if even though you have the solution, but in the geometry, it is nature is different, irregular geometry is there, it is required to apply the finite element method. Not only these things, suppose you have the source and sink in the point of view of engineering or such application. Suppose you have source S1 is source, S2 is sink. If you apply, if you want to use this source and sink in the analytic solution, what we can do, only in the equation we can add the mathematically the source and sink. If we wish to change the place of this source and sink, maybe it is near the source, near the interaction point is here, maybe far. So in that, such kind of study is not available in the analytic solutions, even though you are solving for the spatial problem. So once we talk about the spatial problem, finite element method is applicable. Temporal problem, analytical, or as well as finite difference is applicable. So once we talk about FEM, it is spatial only. A space problem can be handled by FEM. For the time dependent, I repeat, finite difference method and analytic method can be applicable, or any other numerical method can be applicable. So two things: if your geometry is irregular, if the nature of flow or nature of the problem inside the region is different, that in that case finite element is required. We have studied the replacement or the location of the source and sink or any phenomena. So that is also very critical to handle. So very difficult to solve such problem by analytical method, except for very simple shapes. So in that case, and you know, for most of the engineering problem, the shapes are not simple. It is always irregular geometry that we see. So finite element method is very helpful to handle such problems. Okay, so once we talk about the basic approach regarding this method, so again, I told earlier, so what we do here, we discretize the whole domain. This is known as the element. Small pieces, that is known as the element. And once we solve for each and every element mathematically, then we club all the element and we will solve for the whole geometry. Earlier in the mathematics, we have done in the lower level, 10th level or 7th level also, to get the area of some irregular shapes. We apply by pieces, we can have the area, and by joining the area, we can get the area of whole structure. So such things is also same concept we have applied in the finite element method. But the thing is, here area is required, but here we are solving the physical phenomena. It is very easy to say element wise we are having the solution and then we club all the solution. But once we proceed for the actual, it is somehow it is sometimes difficult as well to handle such phenomena. Finite element method of structure analysis was created by academician industrial researchers during 1950s and 1960s. This is all about the history of a finite element method. Sorry. So what we can see, the actual physical system that you can see here, and it is a finite element model that we define in such a way. So whole structure that is discretized in the form of element and node. So this is element and this is the edges, that is known as the node. So whole structure is discretized in the form of element and node. So any physical structure that can be discretized in the form of element. So once we talk about the finite element method, so first we identify the problem. We start with the identification of the problem, which kind of problem you are solving. Then the domain. Suppose we are talking about the heat or diffusion equation, but your domain is different. So the nature of solution may be different in such a way. So after identifying the problem and domain, we go for the differential equation, which represent the physical process in the particular domain. And then we start the discretizing that domain. That is the base grid generation that we say, or discretization in the other word we say. We discretize whole the domain in the number of elements. It may be regular, it may be irregular, like that. So this is also beauty of FEM. In the finite difference method, if you required any additional node, in that case you have to rearrange whole the structure. But FEM, the length, width, or area of the element is it may be different. It is not required, it should be regular. So after mesh generation, we develop the finite element equation in the matrix form for each of the element. So once we go for the solution of such a problem, so that differential equation is described finally in the form of matrix form, that we usually say Ax is equals to B. But for every element, if you have Ax is equals to B, suppose we are talking about problem, and then we add all and we will have the global structure. So assembly of such matrix form, or we say the element equation, that is the global matrix we say. It is a part of assembly. After having the global matrix, we impose the boundary condition if it is a steady state problem, and then we solve this global matrix by any iterative method or any well-known method that can be applicable. If it is the steady state problem, then it will be what? It will be the system of differential equation. If it is a steady state, so it is a system of algebraic equation can be obtained. So finally we solve and we validate the solution from the given problem. So validation is also required in that case. Okay. So the physical problem that we see in the nature, it may be the linear, steady state. Coupled equation also can be handled using the FEM. Engineering point of view, in the structural engineering, in the thermal, fluid flow through porous medium or fluid dynamics, in electrical engineering, electromagnetics, everywhere finite element is applicable if you are talking about the engineering point of view. Other than this, we are using in biology as well. So one thing always common, you have the physical problem. If you have the irregular geometry, you can apply finite element method. So that things we should keep in mind. So the geometry is also always important to consider FEM. So such geometry that you can see the axial geometry, the cyclic, repeated element also can be applicable, that these elements are same. Planar, irregular geometry can be used in that form here. So as I told earlier, the second order differential equation can be represented in the different form. So heat transfer, steady state heat transfer that you can see here, torsion of bar if you apply here. Axially loaded bar is also applicable. So in such a way, all in the common, you can see the second order differential equation that you can see. Only the physical process and physical value, the physical law are different in such a way. So it can be applicable in the number of cases, but according to physical problem that we can apply. Some other area, the heat transfer, the flow through pipes, elastic bars, tension of bars can be applicable here. So accordingly, you can study here. So same type of equation can be represent or different phenomena. Okay, so in mesh generation, if your geometry is very complex, so the generation of mesh, or we can say the structural mesh grid, is very important in defining the discretization of the irregular geometry. Unstructured grid also can be used in such a way. So the finite element analysis is widely used because it decides and determines quality of solution. The quality of mesh also decide time required for solution. So that I will come to the later on, how much time we required, how we understand the computational cost on the basis of element estimation or element refinement as well, how we refine the element accordingly. Such few example for the element. Suppose you have the one-dimensional case. So this kind of element you can obtain. One-dimensional line element, we can say. If your geometry is two-dimensional, so two-dimensional structure element can be framed here. It may be square, it can be rectangle, trapezoidal, that can be applicable. In the solid form, in the coordinate system, we can see here the three-dimensional shape. So different application you can see it. If it is a beam problem, pipe problem, a spring problem, it is one-dimensional finite element method can be used. If it is your geometry in the form of membrane, plate, or cell, so two-dimensional space can be used, or two-dimensional FEM can be used here. In the three dimension, the temperature distribution, the displacement, stress, flow velocity can be it is applicable in the three-dimensional case. Other than this, the tetrahedron can be used. Here, what we can see, this is the tetrahedron. It has the node at the end. But here, nodes are given in the every side, at the middle as well. At the middle as well that we can see. So what we see here, 4 nodes are there. Here 10 nodes are generated. So that is very important how element information is required. So here the node is 10, so your matrix is going to be big. Here node is less, so your matrix is going to be small. And the size of the matrix is going to define the computational cost as well. But at the same time, if you have the node in the middle, you can see it is a quadratic in nature. So if your nature is like that, so that can be estimated with the help of quadratic in nature or two linear that you can define accordingly. So once you have either two linear or one quadratic, so it is again you need to check in which condition you will get the proper solution. The hexahedron brick size also that you can see. Pentagons also that you can see. So this is the selection of three-dimensional element according to the geometry, according to the problem that you can take. These are few shapes that you can see for the two-dimensional and the three-dimensional geometry. The triangular, rectangular, these kind of shapes that you can use in the discretization of the geometry. Here you can see the FEM is very widely used in the Azure problem. So the crash analysis of a car that can be studied with the help of finite element analysis. So this structure cannot be handled manually. So in that case, computer software is used. So here also we can see the computational FEM is required. These are the few examples where FEM are used in the engineering, especially modeling of gear coupling, can drop test. These are a few examples where FEM is used. It's such kind of structure. Here you can see the temperature distribution can be studied. This is a very irregular shape in nature. So even though you are solving the heat equation or heat convection equation, you require a finite element analysis. Analytically, it is not possible to handle such kind of problems. So once we go for the steps wise how FEM is used. So first is the discretization of the structure. So by discretizing, as I told earlier, you can select the element. The element information is very important. Initially, the element information is very important. The discretization is important. Later on, refinement will be discussed. Then the selection of a proper interpolation or the displacement model. So what we see for the every element information, we require the interpolation function. Sometimes shape function also it is defined. It is required for the each and every element. For each and every element, we required to define interpolation function. So according to interpolation function that interpolation function is defined according to the element information. So it also here we assume the solution must be simple from a computational standpoint, but it should satisfy certain convergence requirement. So in the upcoming slide, I will talk about the convergence requirement. First, we will go through the steps of the finite element method. Then we talk about the derivation of the element stiffness matrix or load vector. These are the words related to different books. Suppose you are talking about the SSRAW, so less technical words are used, but in the mechanical problem, you will see the more technical words are also there. So after defining the element stiffness matrix or load vector, we go for the assembly of all the local matrix, and we frame the global matrix in such a way. And finally, we solve the solution of such global matrix with the help of well-known methods. This is the overall idea of the finite element method. Computation of element strain and stress can be used. So any analysis for the completeness, for the compactness, for the convergence criteria that can be applicable. Once we go through all the points, then finally analysis of the result is also required. So the completeness, compactness, and convergence is also required to study. Suppose we are talking about such kind of governing equation. So L5 plus F is equals to 0 with the boundary condition. So in most of the engineering phenomena, the governing equation and the boundary condition is required. Here I am talking about only the steady state problem, because a finite element is related to only a steady state problem. If you have the time dependent temporal problem, so first you can handle the separately you can handle the time, and separately you can handle the space. Time can be handled by having the analytic approach also, Laplace transform or finite difference numerically that you can apply. So such kind of governing equation you can see in the elastic problem, thermal problems, in many more. What we study accordingly you can see. So once we go for the matrix form, Ku is equals to F. So it is a coefficient matrix. This is the column vector that we have, that is unknown vector that we require, and according to available information that we get here. So K, that is if you are talking about the elastic problem, so K can be defined as a stiffness matrix. U will be displacement vector, and the force vector that you can study. So these are the terminology that are used in the different type of problem, but the nature overall idea mathematically we can understand in the same manner. For the thermal point of view, it is a conductivity, it is a temperature that is required to get, and the source according to boundary condition that can be applicable in the right hand side. So these are the terminology that I use for the different areas, but we are solving the same equation in the same manner. Sometimes we do mistake. Elements are of the wrong type. So the cell or element are used where solid elements are needed. So misinformation leads to the maximum error. So I told earlier, the nature of element, the selection of the element is very important to proceed the finite element method. If your information are insufficient, then you will get the maximum error. Some direct method are also used to solve the final system of equation. Some iterative method are also used to solve such methods. So according to problem, you can select. As we know, there are more advantages of FEM. You can discretize the geometry. With the complex, you can handle the complex problems. Sometimes it is easy in nature to solve. Sometimes definitely if your differential equation is complex, so your solution will be different. Solution selection of the element information is also makes you the easy or hard to solve. But finally, what we see, the FEM always give you the approximate solution. Sometimes finite element method is also known as semi-analytic method. It is more accurate than other methods, but you can get the inherent error as you see if information is missing. So some error can be generated. So these are the drawbacks or disadvantages of the finite element methods. I have listed some application of FEM method in engineering, in geomechanics, in civil engineering, in biomedical engineering. Everywhere you can use the finite element method accordingly. Okay. Now, one problem that I will try to solve with the help of finite element method. Suppose we are taking here the diffusion process in the form of a steady state approach only. So for this, suppose we have this is the solution region in the one dimension case, and we discretize this length. C is equal to 10 and dc by dx is equal to 3. That is the given your boundary conditions. And we discretize this solution region with the help of 5 nodes and the 5 nodes that we define, and number of element is 1 less, it is 4. You can extend this 5 to 50, 500 according to problem. So one element information can be generated. So for every element, it has 2 nodes, 1 and 2. So locally, for every element, you have 2 nodes, 1 and 2. But in global form, for every element, the node information is different. Suppose we are talking about here. So it has the global node, it is 3 and 4, but locally it is 1 and 2. So once we are solving local in nature, node information will be 1 and 2, but once we assemble, it has the position between 3 and 4. So this is the third number of element that we are talking about. So accordingly, we will handle all the element. So number of elements are 4 here, 1, 2, 3, 4. You can extend accordingly. To understand the finite element method, we have used the most simple problem. Now, after defining, we define the interpolation function. Okay, So the node information accordingly x1, x2 that can be defined. Okay. So the interpolation function that we defined here, n1c1 plus n2c2. It will lie between 0 to 1 that you can say accordingly. Okay. C is equals to n1c1 that can be represented in the form of matrix n1, n2, c1, c2. This is your problem that we have defined. What is n1 and n2? N1 is what? X2 minus x by L. L is the length of the element. And n2 is what? X minus x1 upon n. So you can see if x is equals to x1, the total length that will be there, x1. So that can be defined in the form of this one, in this way. And n2 for x is equals to x1, it is 0, and then x is equals to x2, it is L. So it will define in such a way. With the combination of these two, we frame the what? Interpolation function for the one-dimensional case. Now this diffusion equation can be defined in such a way: d by dx, dc by dx plus q is equals to 0. After defining the interpolation function, okay, this c is now written as in the form of nc. So in the place of c, we can have the nc. This is the single element information. There are a number of ways to get the weak form of the equation, such like weighted residue method, Galerkin approach, Ries approach. So according to the equation, according to mathematical model, you can go through accordingly. First, I will see here the weighted residue method to have the information for the each and every element. So in the place of C, we write here NC in the interpolation of polynomial form. Once we write NC, it will have some error, so it cannot be equals to 0. So what we see, some residue that we can define here. So in the weighted residue, if we have integration of WR dx is equals to 0, so it can be represented in the form of weak form. So R is replaced by this one. Okay. Now we will see the Galerkin method here. In the Galerkin method, in the place of W, we have used here N transpose. N is the matrix that was represented by N1, N2. So this is a difference between weighted residue and the Galerkin method. So now, according to this formula, the integration by part that we can, integration of UV that we can see here. So integration of UTV that can be applicable here. U is what? U is NT, and dV is what? This whole term that we can represent as a dV, and this is your U. So by having this, what we get, this formula we have used here. And plus integration NTQ dx that we can see. So by solving this, we get this information. Integration of d by dx NT d dNCx dx, it is what? It is integration of NTQ dx plus NTD dNCx upon dt. For some boundary condition can be applicable. So what we see, according to this, the derivative. Now N can be written in the form of matrix form. So N transpose also can be written in the matrix form. So N transpose, that is N1, N2, dNC upon dx. So d upon dx, NC is what? N1, N2, that can be written N1, N2 and C1, C2 dx. So what we have done here, the whole problem is represented in the form of matrix here. Now, this can be written as, if your function is smooth, so it is integration, we can write d upon dx n1, d upon dx n2, and this can be written in the form of d of n1 dx, d of n2 dx, and c1, c2 that can be handled here. Finally, the whole matrix, once you multiply these two, it can be written in the form of integration of dn1 x squared dx. So multiplication of these two, then these two, and accordingly matrix multiplication is applicable. So finally, it is what we get. It is in the matrix form we get here. It is only AX I have written. Later on, we will go for B. Okay. So, you know, N1, N2 is defined in such a way. So dN1 upon X is minus 1 upon L. dN2 upon X is 1 upon L. So accordingly, you can define here. So integration of dN1 upon dx square dx is 1 upon L. And same way we can write here. Now, for every, it is for C1, C2 that we can write for the one element. If you go for the globally, so it is 1, it is 2, it is 3. So it can be changed. C1, C2 can be changed by C2, C3. And this matrix is common for each and every element here. Now the second part, integration NTQ dx was left. So it is what Q integration of N1, N2 dx that we can see. So it is what Q integration of N1 dx and integration of it should be N2 dx. So it will be what? It is Q L by 2, Q L by 2 that we can write here. So by having 1 and 2, what we get? The matrix information for one element that we get here information in the form of matrices. Now it has some value. D has some value. Q has also some value. So what we get here for element 1, it is written as 1 upon L minus 1 upon L minus 1 upon L and 1 upon L that you can see here for the first element. If you go for the second element, what we get, everything is same, only the information of the element is changed. From C1 to C2, it is what? It is the for second element, so it is C2, C3 that can be written here. And the same process is applicable for all 4 elements. Can I? Just a minute. Okay. Same way, you can go for the element 3 and 4. So in this way, we will have the element information for each and every element. Now, the next term is what? Assembly. So the local matrix can be defined here. So you can see D is multiplied by each and every term. So what we see, for every element, we will have the coefficient matrix in such a way. Now the next is we have to assemble all the local matrix and we have to frame the global matrices. So some animation we can do here. So it can be added here. So as you know, it is the element information for 1 and 2 and 3, 1, 2 and 3. This third will be there. So it can be increased. It is by 4 and it is by 4. So all information is added accordingly. So what we see, the nodes are there. So nodal information globally that we have obtained by assembly of the matrix. And in the right hand side also the same manner we will give the values. So this is in the form of that we can say AX is equals to B. So mathematically we understand AX is equals to B, and for the engineering point of view it has a different name discussed earlier. Now we apply the boundary condition. C1 is given is what? 10. So it is 10 and TC by dx is equals to 3. So that is dQL. Sorry, QL by 2 plus 3 that is added here. So once we solve this system of equation, we will get the element information for whole 5 nodes. So in this way, we can obtain the value or solution for the all 5 nodes. The some error can be definitely have some mistakes can be done. Okay, so in last few minutes, I will talk about the convergence of the method. So approximation of the element is very well defined according to finite element method, but the thing is your solution should be converged. The convergence of the solution is very important so that it will match with the exact solution or it is close to the exact solution. So mesh refinement can be done. The one way is mesh refinement can be done. Some necessary condition for the FEM method to converge as follows. The continuity. The trial solution and the weight function are sufficient continuous. As you know, the element information that we say, if it is linear, then it can be written as U is equal to C1 plus C2x. It is continuous in nature. You can write C3x squared if it is quadratic form. If you are writing here. Second thing is completeness. So the trial solution and the weight function must be able to capture a given smooth function with arbitrary accuracy. So the kth degree of freedom that is required according to the problem. So what do we see? Suppose A1 plus A2x or C1 plus C2x is written. It has the first degree of freedom. So number of it has a linear completeness that we can say. It can represent any first degree linear polynomial. Same way, if we go for the quadratic, the second degree polynomial, so it will have the second degree completeness. It can represent the quadratic polynomial. It means what? The function itself and its derivative is also continuous. Accordingly, that can be handled. But if we write in that way, A0, A1x and A2, x4 is the first degree completeness, because it cannot represent all the quadratic, cubic and quadratic polynomials. So this approximation will converge as fast as a linear approximation. So that can be think of the according to element information, you can talk about the convergence. Now come to the refinement. Some finite element analysis is also required. So number of type of refinement can be done here. One is H refinement. If we reduce the size of the element, then you can refine accordingly. P refinement is what? If you increase the order of the polynomial on an element, linear, quadratic. So it refers in this way also you can refine the element information. R refinement is what? Rearrangement the nodes in the mesh. If you shifting the node accordingly, so it is according to the this one also you can refine. One is HP refinement, the combination of H and P refinement, that will be a better result. But once you refine the element information, you must think about the computational cost as well accordingly. Suppose we talk about this kind of information. What we see here, the 4 nodes are there and 2 elements are there. But you have increased the number of elements. So it is 1, 2, 3, 4, 5, 6, and 7, 8. So in the same structure, you have defined the 8 number of elements. You can increase, it is a 32 elements. It is 32 elements accordingly. So the mesh refinement can be done in such a way also. But the thing is, what we see in each and every refinement, the original node is not replaced. Original node is together, even though you have increased the number of elements. But the next, what we can see here, the 6th element is there.